Resonance is one of the most powerful and universal phenomena in physics. In microwave engineering, it is the absolute foundation of how we generate signals, filter out noise, and stabilize frequencies. If impedance matching is about getting a wave to travel from point A to point B smoothly, resonance is about trapping a wave in a box and forcing it to fold back on itself perfectly. The core concept, energy ping-pong. To understand resonance conceptually, think of a child on a playground swing. The swing has a natural frequency, a specific rhythm at which it wants to swing back and forth, dictated by the length of the chains and gravity. If you push the swing randomly, it jerks around and goes nowhere. If you push it exactly at its natural frequency, your small pushes perfectly add to the swing's existing momentum. The energy builds and builds, and the swing goes higher and higher. This is constructive interference.
In an electronic circuit, the swinging is the continuous transfer of energy between two different states: electric field energy, stored in a capacitor, or the physical gap between conductors; magnetic field energy, stored in an inductor, or the physical flow of current through a conductor. At the resonant frequency, F0, the physical structure perfectly balances these two energy storage mechanisms. The energy sloshes back and forth between the electric field and the magnetic field, completely in sync. The most important metric of any resonator is its quality factor, Q. It measures how well the resonator traps energy versus how much it loses to heat or radiation per cycle. Q equals omega times maximum energy stored divided by power dissipated per cycle. A high Q resonator acts like a tuning fork made of perfectly pure crystal. It rings for a very long time at one incredibly precise frequency. A low Q resonator acts like a tuning fork made of wood. It makes a dull thud across a wide band of frequencies.
2. Taxonomy of resonators. As we move from low frequencies, audio, radio, up to extreme microwave and millimeter wave frequencies, the physical size of the waves shrinks. Because resonators must be sized relative to the wavelength, the physical architecture of how we build them changes drastically. Here is a look at the different types moving from lowest frequency to highest. A. Lumped element resonators, RLC circuits. How they work: the classic inductor, L, and capacitor, C, wired in series or parallel. Energy sloshes between the coiled wire and the parallel plates. The resonant frequency is exactly where inductive reactance cancels out capacitive reactance. F0 equals 1 over 2 pi square root of LC. The catch: at microwave frequencies, real inductors and capacitors stop acting like ideal components. The wires radiate energy like antennas, and parasitic effects ruin the Q. Therefore, standard LC circuits are rarely used above 2 GHz.
B. Planar transmission line resonators, half wavelength and a quarter wavelength. How they work: instead of separate capacitors and inductors, we use the distributed capacitance and inductance of a microstrip or strip line trace. If you cut a piece of microstrip trace so it is exactly 1/2 wavelength long and leave both ends open, unconnected, a wave will bounce back and forth between the open ends. Because it is exactly 1/2 wavelength, the reflected wave aligns perfectly with the forward wave, creating a massive standing wave. Use case: this is the basis of many printed circuit board filters. You place multiple half-wavelength traces next to each other, and they couple their resonant energy together to form a bandpass filter. They have a moderate Q, typically 50 to 200, limited by the loss tangent of the PCB and the skin effect in the copper trace.
C. Metallic cavity resonators. How they work: a hollow block of highly conductive metal, like silver-plated copper or aluminum. You inject microwave energy into the box through a small probe. If the dimensions of the box perfectly match a multiple of the half wavelength in 3D space, the electromagnetic wave bounces off all walls in perfect harmony. Use case: because there is no dielectric substrate to cause molecular friction, and the large metal walls offer huge surface area for currents to flow, reducing skin effect losses, cavity resonators have massive Q factors, often 5,000 to over 20,000. They are used in high-power radar, satellite multiplexers, and particle accelerators.
D. Dielectric Resonators, DRO. How they work: a small puck-shaped cylinder made of a highly specialized ceramic material with a massive dielectric constant, epsilon r, between 30 and 100. Because waves travel much slower inside this dense puck than in the surrounding air, the electromagnetic wave reflects off the inside boundary of the puck, total internal reflection.
The wave is essentially trapped inside the ceramic without needing metal walls. Use case. Because the waves are shrunk by the high epsilon R, these pucks are incredibly compact, but offer cavity-like Q factors, 5,000 plus. They are used in dielectric resonator oscillators, DROs, to generate extremely pure, low-phase noise microwave signals for communication base stations.
E. Acoustic Resonators, SAW and BAW. How they work. This is one of the greatest tricks in modern engineering. Electromagnetic waves at 2 GHz have a wavelength of about 15 centimeters. A half-wavelength resonator would be 7.5 centimeters long, way too big to fit inside a smartphone. Acoustic resonators use piezoelectric materials, like aluminum nitride, to convert the incoming microwave electrical signal into a physical, mechanical sound wave, a vibration in the crystal lattice. Sound travels about 10,000 times slower than light. Therefore, the acoustic wavelength is 10,000 times smaller than the electromagnetic wavelength. We build microscopic mechanical resonators, surface acoustic wave, SAW, or bulk acoustic wave, BAW, that resonate at the microwave frequency, but take up almost microscopic physical space. Use case. Every single smartphone on Earth contains dozens of BAW-SAW resonators acting as perfectly tuned microscopic filters to separate 4G, 5G, Wi-Fi, and Bluetooth signals.
YIG Resonators, magnetically tunable. How they work? A microscopic sphere of yttrium iron garnet, a synthetic crystal. The electrons in this crystal have a magnetic spin. If you place this tiny sphere in a strong external DC magnetic field, the electron spins align. When hit with microwave energy, the electrons precess, wobble like a spinning top, at a very specific resonant frequency. The magic: you can change the resonant frequency of the YIG sphere over a massive range, e.g. 2 GHz to 20 GHz, simply by changing the strength of the external DC electromagnet. Use case: highly sophisticated ultra-wideband tunable oscillators for electronic warfare and high-end spectrum analyzers. Enjoying this? Smash that like button and subscribe for more RF and microwave engineering content. Drop a comment below with what you want to see next. I'm reading every single one. Let's get back to it. Thank you.